Today I'm going to show you kind of a cool simulation we can do in R and Switchboard to help us think about the ways in which sampling variation gets larger as we ask increasingly complex scientific questions. So the idea here is that when we're doing fruitful science, one question leads to another, and often the questions we ask become more complex. So we might start with something kind of simple, like we might ask, like, is there adult neurogenesis in the hippocampus of rats? And really, we're just observing what's the typical level of neurogenesis. So it's just a single mean we might be interested in estimating. But if we do find that, yes, there is adult neurogenesis, then we start thinking about, well, what are the factors that control it? I wonder if stress might control it. So then we might want to start comparing between groups. We might want to look at the control group and their neurogenesis and a stress group. And now what we become interested is the difference between two means. So we've gotten up a level of complexity in the question we're asking. And if we find out that, yes, stress influences neurogenesis, maybe it completely blocks it, then we might be interested in knowing why does it block it? And we might want to dissect that effect. So we might want to, I don't know, change cortisol levels or remove the adrenal gland to see if that blocks the ability of stress to block neurogenesis. So now we've gone up another level. We've added, we're at a factorial experimental design, and the research question we are interested in is now the difference between your stress effect under normal conditions and with the adrenal gland removed. And so now you're looking at an interaction, and that involves differences between 4 different means. So as your research program progresses, you're making increasingly more complex questions that you want to ask. And let's simulate what this does to sampling error, to the standard error of the mean. How does that complexity influence the precision with which we can obtain results from an experiment? So what I'm going to do is we're going to simulate this in R, and we're going to use this cool switchboard package I just became aware of by Mark Longinese. I'm not sure if I'm saying that right, and I'll show you what we're going to do. It's really, really simple. In R, we're going to just collect, we're going to draw random samples from the 4 cells in a 2x2 experiment. We're just going to draw 5 samples in each cell. And after we do that, we're going to calculate some effect sizes. We're going to get the mean for a single cell. Then we're going to get some simple effects. What does stress do under normal conditions? What does stress do whenever we have stabilized cortisol? And then we're going to be able to do an interaction, the difference between those 2 simple effects. So we are just making up some fake data using the rnorm function in R. Then we're calculating some effect sizes. And what I've done here is I've made it so that the cell mean, the amount of neurogenesis in a normal animal, is 3,500 new neurons. And then we are imagining that stress completely blocks that. So it goes from 3,500 to 0. So the difference between them is also 3,500 neurons. And then that the stabilizing cortisol, by removing the adrenal gland, completely blocks the stress effect. So we go from 3,500 neuron reduction due to stress to no reduction whenever cortisol is being replaced. And so the interaction is also 35. You can use whatever numbers you want, but the key thing here is that our effect sizes are on the same raw score scale. So we can plot them all next to each other and compare them visually in raw scores. We don't have to think about standardizing or anything like that. Once we've simulated and calculated our effect sizes, we're going to use Switchboard to visualize this. And there's some more complexity to this, but this is just kind of like pseudocode of what it does. Is that one of the main things in Switchboard is this idea called an eavesdropper, where you just basically pass it a variable that you want to eavesdrop or visualize repeatedly with each draw of the simulation. So here you can see I've got one that's going to show us the value of the single mean, the value of one of our simple effects, the difference between 2 means, and the value of the interaction. So we get 3 different panels. They're going to be able to monitor the simulation. So let me bring it up here, and I can show you what it looks like. Here, this first panel is the single mean, and when I turn it on, you can see that we're doing repeated draws, and even though the population value is 35, of course, samples don't perfectly reflect reality. They give us useful but imperfect knowledge about the real world, and so we see this dance of the means, this variety around the real truth of 35, with some samples overestimating and some underestimating, and we could think about that standard error, the fact that there is sampling variation or sampling variety. Now let's look at the mean difference, which also has a value of 35. And so we're also going to see that dance around 35. But right away, you can see that this dance is more erratic, that there's a lot more variation from sample to sample, about 40% more. And if we turn on the interaction term, which also is going to dance around 35, now we can see a really much wider level of variation from sample to sample. We can see that given the same exact cell size, the interaction is a lot harder to estimate. There's a lot more sampling variation. Of course, we do know this. You can see the math right here, that our standard error for a single cell is the pooled standard deviation divided by n and then take the square root. Whereas for a difference between two means, assuming equal cell size, we have to add that pooled standard deviation divided by n up for each cell that's involved. So it becomes twice as big before we take the square root, or square root of 2 larger than a single cell, 40%. And for an interaction, we have 4 different unknowns. So we have that term 4 times. And so after we take the square root, our standard error becomes twice as big. I just think it's really cool that with just a few lines of code, though, you can see it, and then you can play around with it. So we can add a slider here. This is just 5 samples per cell, pretty small, but the pattern, or the fact that sampling error grows with measure complexity, is consistent no matter what our sample size, right? So I could dial my sample size up, and of course, all my standard errors shrink, but you can still see the overall relationship, that now we're estimating a single mean really precisely, but 40% less precisely with the mean difference, and twice as fuzzy or error prone in the interaction. That's not going to go away even with sample size. And what this tells you is you've really got to carefully match your sample size to your research question. That sample sizes that worked for just documenting a phenomenon are not always adequate for comparing a phenomenon between groups, and are especially inadequate for more complex research questions that involve interactions. And there's this really cool tool called interactionpower.com that you can go to, and you can draw a predicted interaction, and you can get an idea about what sample size you'd need should you want to conduct a straight up hypothesis test for it. Weaker the interaction, sometimes extremely disappointing or intractable sample sizes. So that's it. And I just want to kind of show that it's a neat way that you can use R to simulate, and that cool switchboard program to help you build your intuitions about how sampling variation works.